For problem 7.125, we have this circuit here on the left. I have like several copies just in case we need to use it again. But this is the circuit that we have. So it's an NPN BJT, right? And we have a DC bias circuit that uses this R1 and R2 here to provide a voltage at the base and basically a current at the base, right? And one thing that we need to remember is that for a DC analysis, that's the first part of the problem, those capacitors here, they become an open circuit. So we don't have this load connected to the collector, this load here. We also don't have the V signal here connected at the base, and we don't have the emitter grounded. Okay, so for DC analysis, that's not happening. Okay, and if we consider those values here for the components, so R1 equals 27K, R2 equals to 15K, RE equals to 0.4K, RC equals to 3.9K, and beta equals to 100, part A asks us to find the collector current. Okay, so one thing is that first let's analyze this part here at the base. Okay, so this particular part we can represent as a voltage source of VCC. So in our case, VCC is 15 volts. And then we have R1 here, R2 here, and that goes to the base, and this goes to the ground. So this is R1, this is R2. So you see that in the lecture notes we can use a Thevenin's theorem to basically represent this circuit here at the base using a Thevenin's equivalent circuit, which is just a voltage source in series with a resistor, and that goes, so this is the base, this is the ground, right? So let me put the ground here and here, and this is V Thevenin, okay, and this is the base. So if we look at this circuit, I mean, we want to simplify this one here to this one there by using Thevenin's equivalent circuit. So to simplify the circuit that's connected to the base, okay? So if we calculate the Thevenin's resistance of this particular circuit, we know that we need to short circuit this voltage source. So if we see the resistance from these terminals here, it is just R1 in parallel with R2, which gives us R1 times R2 divided by R1 plus R2. So if we plug in the values of R1 and R2, we get a Thevenin's resistance that is 9.643 kilo ohms. So that's the Thevenin's resistance. And if you want to calculate the VOC, or the Thevenin voltage, is just this voltage here, which is the voltage across this R2 here. Using a voltage divider, we can calculate that voltage, right? So VTH is equals to the VCC times R2 divided by R1 plus R2. And that gives us a voltage, Thevenin voltage, of 5.357 volts. Okay, this is 15 volts, and this one's here is 27. This one here is 15. Okay, this one is 27K, this is 15K. So if we plug in those values, we will get this 5.357. So at the end, this entire circuit here for the DC analysis, okay, can be converted to a circuit that is just a, so now this voltage applied at the base is different from the voltage applied at the emitter, the collector, sorry. So this one here is still 15 volts, but this one here is now 5.357 volts. And this resistance here at the base is that 9.64. Let me just zoom in here. 9.64 k ohm. This is still RC, which is 3.9 k ohm. This is still RE, which is 2.4 k ohm. Okay, so that's the circuit. Sorry, that's the circuit that we have. Okay, and now we can assume. So we can assume active mode operation, and that tells us that VBE is equals to 0.7 volts. So this voltage here, it's 0.7 volts. Okay, and then we can apply a loop analysis here at the base emitter side, and that gives us minus 5.357 volts plus 9.64 k times IB plus 0.7 plus IE times 2.4 k ohm, and that equals to 0. Now remember that the current at the base is equals to the current at the emitter divided by beta plus 1. So if we plug in this equation here in IB up here, we basically can isolate, so we get IE that multiplies those 2.4k, plus now we have IE here in IB that multiplies those 9.64k divided by beta plus 1, right? And that's equals to minus 5.357 plus 0.7. Okay, that goes to the right hand side as 4.657. So in the end, IE is equals to 4.657 divided by 2.4k plus 9.64k divided by beta plus 1. And you know that beta is 100, so this is 101, which gives us a value of the emitter current. The emitter current equals to 1.86 milliamperes. So this is IE. So let me just put this part B here down there. So let me just move it down here. And we know that IC is equals to alpha IE. Okay, so IC in this case, alpha is 100, beta divided by 101 times 1 over 1.86 milliamperes, which gives us IC equals to 1.8477 milliamps. So that's IC. So part A, we are done. We calculated the value of the collector current. Okay, and we need the value of the collector current along with the transconductance and beta to calculate the parameters for the pi. So the hybrid pi model, or the pi hybrid model for part B. So in part B now we need to use the P hybrid model to determine the input resistance. Okay, so the input resistance and the overall voltage gain, which is V out over this signal. This is the overall voltage gain. if the source resistance, okay, the signal resistance is 2k ohm and the load resistance is 2k ohm. So now we are going to perform a small signal analysis and or like a very high frequency signal. So this capacitor here becomes a short circuit, this capacitor becomes a short circuit, and this capacitor becomes short circuit. So it means that the emitter resistance is no longer connected at the emitter. We have the emitter here grounded. Okay, and the hybrid pi model. So it's this model here. Okay, this is our pi. This is plus minus V pi or VBE, small be, and this is the current at the collector. Here's the base, here's the emitter. Gm times V pi or VBE. Okay. Now we know that R pi, in this case, R pi, well, let's start with Gm. So the transconductance, Gm, is equals to the collector current divided by the thermal voltage. Now the collector current, we know that's around 1.80, so let me see, 85 milliamps, divided by the thermal voltage. It's not given, so we consider 25 millivolts. This gives us a transconductance of 74 milliamperes per volt. Now that we know the transconductance, we can calculate R pi. So R pi is equals to beta divided by transconductance, and that's equals to 100 divided by 74 milliamperes. And then R pi is 1.35 kilo ohms. So those are the two values that we need to complete our hybrid pi model. Now, so now that we have this hybrid pi model, again for small signal analysis, this is grounded, this is a short circuit, this is a short circuit, this voltage source, this one here, they all goes to the ground because it's just like high frequency analysis. So we ground, we short circuit all the voltage, DC voltage sources that we have, and our circuit, it becomes this circuit here. So we have our V signal that's connected to our signal. Then we have R1 that goes to the ground. We also have R2 that goes to the ground. And we also have, so here it goes to the base, right? So it connects to the pi hybrid model. So here we have R pi. And remember that from R pi we go directly to the emitter, and the emitter is grounded. So this one here, if we want, we can redraw this as another resistance that goes directly to the ground, which is R pi. And this potential here is V pi or VBE. Okay. And we also have a current source that connects to the emitter, which is grounded in this case. Then we have the collector. So this is the collector node. This is the base node. And here we would have the emitter, but the emitter is grounded. So this is RC. And now we have also the load here connected to the same node as RC. So we have the load here. This is RL. So that's the circuit, the small signal circuit that we have based on this biasing circuit and this circuit for using this NPN transistor. Now, one thing is that the input resistance, so the input resistance is the resistance seen from this terminal here. So after the signal resistance, so is this resistance here seen from this terminal. And if you look at this terminal, basically our input resistance is R1 in parallel with R2, right? Those two here. And that in parallel with R pi, right? So that's what we have. And this is the same as 1 over R1 plus 1 over R2 plus 1 over R pi to the minus 1 here, right? We need to invert. So if we substitute here the value of R1, that's 27 kilo ohms, the value of R2, that is 15 kilo ohms, then the value of R pi, that in our case is 1.35 kilo ohms, we get our input resistance as 1.1842 kilo ohms. Okay, so that's the input resistance. Now we need to calculate the overall voltage gain, right? So the overall voltage gain, we can first define V pi over V signal. So if we look at V pi over V signal, right, this is V pi, okay, and let me zoom in here. So here the current is GM V pi or VBE, okay, it doesn't matter, it's just the way we call it, this potential difference here. So if we look at this circuit, this part of the circuit here, because we calculate this input resistance, it's just the same as drawing this circuit here, right? This is our signal, this is our in, and because all those three resistances here, they are in parallel, V pi is the same. So V pi is the same as the voltage across R in. And we can apply a voltage divider here to calculate V pi. So V pi is equals to V signal times the input resistance divided by the input resistance plus the signal resistance. And if we isolate V pi over V signal, this gives us the input resistance divided by the input resistance plus our signal. So that's the first input gain. If we substitute the value of R in and R signal, we basically get 1.18 divided by 1.18 plus 2, right? 1.18k divided by 1.18 plus 2k, and this gives us 0.371 volts per volt. So that's the first gain that we have. It's not the overall voltage gain, but remember this equation here, V pi over V signal, and that's the value of that. Okay. Now the second part is defining an equation for V out over V pi. Okay, so if I go back here in the circuit, so let me simplify the drawing here, or let me just draw down there this part of the circuit. Okay, so for the second part, we have this current source that goes to the ground. Here it connects to RC. Here it connects to our load. So this is our load, this is RC, and this is GM times V pi amperes, right? It's the value of this, the current provided by this controlled current source. And V out is this voltage here. Now because we are measuring V out with the polarities plus and minus here, we can write that V out is equals to this current here, right, times the parallel of RC with RL. Okay, because that's the voltage across V out is the voltage across the parallel of RC and RL. So if we take the minus here, because the current here GM V pi is forced to go in this direction, so minus 2 to plus here, so it's minus GM V pi times RL times RC. This is the parallel, right? L plus RC. And if we plug in the value, so we can isolate V naught over V pi, that's equals to minus GM RL RC RL plus RC. If we substitute the values of GM and V and RL and RC, we get minus. So GM is equals to 74 milliamperes. RC is equals to 3.9 kilo ohms. 3.9 kilo ohms times the load resistance. So the load resistance is now 2K. So times 2K ohm divided by 3.9K plus 2K ohms. This gives us V out over V pi equals to minus 97.83 volt per volt. Now remember that we need to define V out over this signal. And if we look up here, we have V pi over this signal that we calculated before. If we multiply that by V out over V pi that we have here, basically V pi here cancels with V pi there, and then we got the overall voltage gain, which is those 0.37 times those minus 97.83, which gives us a V out over this signal equals to minus 36.29 volt per volt. Okay, so that's it for this problem.